Okay, kids, today we're going to talk about kinetic energy, the root mean square, and Graham's law of effusion. And this is all related to gases, okay, and how they behave. The first thing I'm going to touch upon briefly, we're going to go more into it in the next video, is just kinetic molecular theory. We assume that in honors chemistry that all gases are what's called ideal. And an ideal gas just follows certain behaviors, certain rules. And these rules are called the kinetic molecular theory. So these are some assumptions we make when we talk about an ideal gas and when we use the ideal gas law. Okay, now, just like in real life, not everything is ideal, and gases are not ideal in real life. Okay, but these are the assumptions we make. And we first talk about gases to be point masses, meaning they have really very small mass. We don't even look at their mass. Okay. We also talk about their kinetic energy. Remember, we're going to talk more about it in the next slide, but kinetic energy is a function of temperature. And as temperature increases, kinetic energy increases. As temperature decreases, kinetic energy decreases. Okay, and we can also assume that the average kinetic energy of a gas, any gas, at the same temperature is the same. And then gases also, when they move in a straight line motion. Okay, a rapid, random, straight line motion. Okay, so, and number 4 is that the volume of the gas molecules, if we picture them so small in the container, that we picture the volume of the container being big compared to the gas molecules themselves. So we assume that the volume of those little molecules in there is negligible. And then another thing we assume is that the attractive and repulsive forces is negligible, meaning the gases are elastic. They don't stick together. No sticking together. Okay, so these are 5 assumptions that we make when we talk about an ideal gas. And we're going to get into that more tomorrow where we talk about deviations from ideal. So let's go into kinetic energy because it's very important because gases have a lot of kinetic energy. Okay, the formula for kinetic energy and the definition is kinetic energy is 1/2 times the mass times the velocity squared. Okay, kinetic energy we call the energy of motion. Okay, so it has a mass component, which is in kilograms, and it has a velocity component, which is in meters per second. Okay, now the above formula is for one atom or one molecule. Okay, but what about a mole of gas? How could we calculate the kinetic energy for a mole of gas? Remembering that a mole is equal to the mass over the molar mass. Okay, so if we take this and rearrange it, and we assume it's for 1 mole, then we can use this formula for 1 mole of gas. Kinetic energy is 1/2 the molar mass times the velocity squared. And now we are calling V, instead of V, we're going to call it mu RMS, which is now called the root mean square, which is the average speed. Okay, so this is the average speed. Okay, so now we are going to look at the formula for average kinetic energy of all the gas molecules. Okay, this is our chemistry formula. And it's 3/2 times R times T, where R is 8.314. Okay, and the units of R are going to be joules per mole per Kelvin, okay, which will go into how that translates to kinetic energy. Temperature is always in Kelvin when we work in gases. And as we can tell from the formula, that kinetic energy, since it equals 3/2 RT, is directly related to temperature, since R is a constant. Gases at the same temperature have the same average kinetic energy. Now, what we can do is take the two formulas we just looked at, okay, the 3/2 RT and the 1/2 times the molar mass times the root mean squared. And you can tell that gases at the same temperature have the same kinetic energy, which we just saw. But when they have different molar masses, they have different speeds. So the heavier the gas, the slower the speed, and the lighter the gas, the greater the speed. But at the same time, it compensates each other, and they end up having the same kinetic energy if they're at the same temperature. Okay, now, if we take these two equations that we just got for kinetic energy, and we cancel out the 2's and rearrange, okay, you can get this root mean square formula. Okay, so let's look at that real quick. So if we have 3/2 RT, and that equals 1/2 the molar mass times the root mean squared, okay, we can cancel out the 2's, and if we solve for molar mass, excuse me, if we solve for root mean square, we end up with this equation down here. And the mass has to be, so that molar mass has to be in kilograms per mole to cancel out the units. And the temperature, of course, has to be in Kelvin. Okay. Now, just for a side note, I'm just going to show you how the units work out to cancel when for this type of problem. Okay. So you may picture, well, how does joules per kilogram cancel out? Okay, so we have our root mean squared formula, okay, equal to the square root of 3 RT over the molar mass. Okay, now if we put our units in for this, okay, we know we have just units. We're going to have the square root of 3. Well, we're not going to put numbers in. We're just going to put units. We have joules. The units of R are joules per mole. Okay, over Kelvin. And then, of course, the temperature is in Kelvin. So we can see right there that these units actually cancel out. And then on the bottom, we have molar mass, which we said has to be in kilograms per mole. Okay, now what we're left with, these moles cancel out. What we're left with is the square root of joules per kilogram. Okay, so now we're left with that. Now, how is that equal to meters per second? Okay, so well, here's what happens. So we have root mean square equals the square root of joules per kilogram. And now we're just going to go into a little bit of physics, okay, where we know work equals mass times acceleration times distance, okay, and that's equal to a joule, which is equal to kilograms times meter over second squared. This acceleration is in meters per second squared. Okay, now we can get the units into the same units as up here. So I'm going to divide both sides by kilogram. And now I get joules per kilogram is equal to kilograms, oh, excuse me, canceled out, I'm going to get joules per kilogram is equal to meters squared over seconds squared. Okay, now if I take the square root to get it into square root of joules per kilogram, look what I have. I have equals meters per second, which is the same thing as speed. Okay, now if you didn't follow that derivation of the units, it's okay as long as you know what units to use to make sure it cancels out. But this is just proving that the square root of joules per kilogram is the same as meters per second, which is what the root mean square units should be. Okay, so let's do some practice problems now. We're going to determine the root mean square of N2 and O2 at 25 degrees Celsius. Okay, so we're going to take the formula, okay, where we have the root mean square equals the square root of 3RT over the molecular weight, or the molar mass. Okay, so if I plug in my numbers, I have 3 times 8.314, okay, times the temperature, and the temperature has to be in Kelvin, so that's going to be 298 Kelvin, divided by the molar mass. The molar mass has to be in kilograms per mole. Okay, so if it's 28 grams per mole, it's going to be 0.028 kilograms per mole. And I get a root mean square of, for nitrogen, this is for nitrogen, of 515 meters per second. Okay, and now I can do the same thing with oxygen. And when I do oxygen, I'm going to do the same thing. Let me move this down a little bit so we have some more room. When I do it for oxygen, I take 3 times 8.314 times same temperature. Now this time the molar mass is, remember, 32 grams per mole, which is going to be 0.032. And you get an answer of 482 meters per second. Okay, so the key to understanding and how to calculate root mean square is, number one, you use the R value of 8.314. Number two, temperature has to be in Kelvin. And number three, the molar mass or molecular weight has to be in kilograms to make the units work out. Okay, so now let's do the next problem. Okay, determine the root mean square of N2 at 100 degrees. Okay, so what I'm going to do is just take away this O2, and now we're going to do N2 at 100 degrees. Okay, so it's going to be the same formula. Okay, the root mean square is going to equal the square root of 3 times 8.314, and at 100 degrees, that's going to be in Kelvin, 373 Kelvin, divided by its same molar mass, 0.028, and that's going to be equal to 576 meters per second. Okay, so we have two speeds. Okay, and our last question asks us to compare those two speeds. Okay, so what does temperature do to the speed? Well, you can see here that 576, first of all, is higher than 515. So what we can learn from this is as temperature increases, the speed of the particles increases. Okay, which means the average kinetic energy is going to increase as well. Okay. Now, let me show you, you can actually put it on a graph, molecular speed. Okay, and this is called the Boltzman distribution. This is called the Boltzman distribution. I don't have the title on it, but okay, so what it's doing is plotting the number of molecules on the left. Okay, so how many gas molecules you have, and then the speed on the x-axis. So the y-axis has the number of molecules, and then the x-axis has the speed. Okay. Now, in this case, this is for nitrogen, and what you do in the blue, you're drawing the curve for the speed curve, the Boltzmann distribution curve for 0 degrees, and then you can see for an increased temperature of 100 degrees is in red. Now, if we look at this, okay, we can see that the area under the curve for the blue line right here, that is showing you the area under the curve represents the number of molecules, okay? And that's not going to change with an increase in temperature. It's just going to shift the curve. So the area under the curve is not going to change between the 0 degrees and the 100 degrees. It's just going to shift the curve over. And what you can see that what happens is with increased temperature, if you look at one higher speed, you can see that there's more particles that go faster at a higher temperature. Okay. And then they can also draw a line for that root mean square on the graph as well. Okay, so the point of this is to show that at increased temperature, you can see that the top of the line goes a little lower and then it shifts to the right. Okay, so what can we conclude from this graph that we just looked at? Okay, not all molecules have the same speed. Okay, they all have different speeds, some slower, some faster. Okay, so when they're colliding, some speed up, some slow down, but the total kinetic energy is constant. Okay, as you increase temperature, you increase speed of these gas molecules, get them more excited, more collisions. Higher temperatures cause higher kinetic energy because the speed increases. And kinetic energy is directly related to speed. Now, what if we looked at a graph for different gases, okay? Heavier gases, lighter gases. Okay, well, remember, heavier gases will move slower. They'll have a larger speed. They can't move as fast as small particles. They'll move much faster. However, smaller molar masses will travel faster at a given temperature. So you can actually compare graphs showing different molecular speeds. And this is a Boltzmann distribution. Instead of showing two different temperatures for the same gas, this is showing you different gases. Okay? And what you can see is that at a particular speed, we'll pick 5 times 10 to the second, you can see that you have at that slower speed, you have more of the heavier molecules at that slower speed. Okay, whereas the lighter molecules have more molecules at a higher speed. And now what we can do is take our equation for root mean square and combine it to get what we call Graham's law of diffusion. Okay, so if you take the root mean square formula for gas at 1 and the root mean square formula for gas 2 and put them on top of each other, remember, it doesn't matter, we still have the same temperature, and cancel these two numbers out, you end up with molecular weight of gas 2 over molecular weight of gas 1. Okay, and that's what we call Graham's law of diffusion, which ends up looking like this. Rate 1 over rate 2 is equal to the square root of m2 over m1. Okay, so I just corrected my slides a little bit, but when you put two gases on top of each other and take our root mean square formula, you end up with rate 1 over rate 2 is the square root of molar mass of gas 2 over m1, which is called Graham's law of effusion. And remember, effusion is just the escape of a gas through a tiny hole. Okay, so if you have a tiny pinhole, it's the rate of escape of the gas through that tiny pinhole. Okay, and you can see that the rate is inversely proportional to the square roots of their molar masses. Okay, so if you look at this example down here, the rate at which H2, which measures 2 grams per mole, effuses compared to O2, which is 32 grams per mole. Okay, and if we make H2 gas 1 and O2 gas 2, you could use the formula square root of 32 divided by square root of 2, which makes H2 4 times faster, which makes sense since hydrogen is a lot lighter than oxygen. Okay?